All right, here we're going to do a section 8.1 on sequences and series. A sequence is a list of numbers, and those lists of numbers will follow a specific rule. The difference between a sequence and a series is that, as you'll find out later in the section, a series is the sum of those terms, and it has a special notation so that you can tell the difference between the sequence and the series. So here we have a rule, a sub n, and a sub n is going to be the rule for the sequence. So if we're trying to find the first four terms, we'll just plug in 1 through 4 for n to get four different numbers. So 3 times 1 minus 1 is our first term. It's going to be 2, a sub 2, 3 times 2 minus 2, 3 times 2 minus 1, rather, which is 5, a sub 3, 3 times 3 minus 1, or 8, and a sub 4 is 3 times 4 minus 1, or 11. So first four terms, that's all you need is right there. Okay, another example of a rule here is a sub n equals 3 plus negative 1 to the nth power. So the exponent here is where you're plugging in the different terms. So if it's first four, again, we're doing 1 through 4. It will specify if you would start anywhere other than 1. 3 plus negative 1 to the first is 2. 3 plus negative 1 to the second is 4. So between those two, the only thing that's going to change is instead of adding a negative 1, you are adding a positive 1, and that's due to the positive or negative exponent on the negative. A sub 3 is 3 plus negative 1 to the third, so this is actually going to be the same as a sub 1 because we're adding a negative 1 instead of a positive 1. So that's 2. And a sub 4 is 3 plus negative 1 to the fourth power, which is going to be the same thing as a sub 2. So our four terms are 2, 4, 2, 4. Okay, another sequence. First five terms, again, it will tell you if you should start anywhere other than 1. So our first term is a sub 1 equals negative 1 to the first over 2 times 1 minus 1, which is negative 1. A sub 2 is negative 1 to the second over 2 times 2 minus 1, or positive 1 over 3. So again, we're seeing the, instead of on the section up a B up here, where the negative ones alternated signs, here we're seeing that the whole answer is alternating signs because the top of the fraction is going to be either a positive or a negative depending on what that exponent is. A sub 3 is negative 1 to the third over 2 times 3 minus 1, or negative 1 over 5. A sub 4 is negative 1 to the fourth over 2 to the 4, 2 times 4 minus 1, or if you're seeing the pattern already, so the signs are alternating, it's going to be a positive 1, and the bottom of the fraction, if you're noticing, is going to now be a 7. It's odd numbers, and they appear to be going up by 2, the bottom of the fractions. If you're starting to see that, I cannot possibly make you show work for every single one because it's can be somewhat intuitive sometimes. Last one. Again, you might have noticed it's going to be a negative, and the bottom of the fraction will be a 9. Okay, the next part of this section is to find what the sequence rule is, which if I think that there's anything that can be challenging about this section, it's finding what the rule is. If you're not given it, you're already given the terms, and you have to figure out what the rule that fits along with that is. So if I have to think of a strategy here, my strategy is to write down what the n's are. So that would be the number of terms. 1, 2, 3, 4. They gave us 4 terms. And then the a sub n's that they gave us are 1, 3, 5, and 7. Now, a goal here is going to be to try to figure out what the relationship is between n and a sub n. So sometimes these are going to come very easily and sometimes they're not. They're going to be related either by addition, subtraction, multiplication, division, or basically any exponent, unfortunately, which means that there is not an easy way to figure this out. So to go from 1, our n value of 1, to the a sub n value that matches, adding 0 or multiplying by 1, but neither of those options would work for the other n values. So we have to think about something else, maybe multiplication and addition or subtraction, something like that. So I guess there's really no other way to explain how to do this other than a guessing and checking option of looking at the multiplication, division, addition, subtraction. So I can see that all of the a sub n values are 1 away from if you were to multiply those n values by 2. That's really the only way to explain that, is you'd have to multiply the n by 2 and subtract 1. Some of you would have gotten that right away. You see it and be like, oh, duh, right away. And some of you are just like, I don't know how you got that. So it's really guess and check. Keep doing a lot of them. See if you can find those patterns. But there's not really a specific way to teach that skill, unfortunately. On letter B, I'm going to do the same thing. Write down the terms, 1, 2, 3, and 4. And I'm going to write down the a sub n's they gave us, 2, 5, 10, and 17, and try to figure out how the n values relate to the a sub n values. If I think about addition right away, from n equals 1 to a sub n equals 2, I'd be adding 1, but that doesn't work for any of the others. Looking for some sort of multiplication and subtraction or addition, just like we did on section on the A here. I don't really find anything that works for that either, but I do see that all of the a sub n's are 1 bigger than if we were to square each n value. So that is saying we square each n value and add 1, that will get us to our a sub n. Again, there's not really a great way to explain that perfectly. Just guessing and checking and figuring out different methods. Okay, the Fibonacci sequence is a very cool sequence that they find a lot of places in nature. I can show you later. We're obviously not going to be looking at any of those now, but there are patterns in flowers, petals, and there are patterns rather in hurricanes. You know, the circular pattern in a hurricane. Some of those follow the Fibonacci sequence. And what I want you to get out of this now is to how to follow a rule like this. Not necessarily to use this anywhere, but to figure out how to apply the a sub k rule, where it's using 2 terms that were prior in the sequence instead of just following one rule and plugging a number in. So find the first 6 terms of the sequence. A sub 0 and a sub 1 are given. So we have left to find a sub 2, 3, 4, and 5. That will give us 6 terms. So a sub 2, if I'm following the a sub k rule, is going to be a sub k minus 2 plus a sub k minus 1. Well, a sub 2 minus 2 is a sub 0, and a sub 2 minus 1, it's a sub 1. So that means I'm taking a sub 0 and a sub 1 and adding them together, and that is my a sub 2. So that's 2. Okay, let's see how that looks for a sub 3. A sub 3 minus 2 plus a sub 3 minus 1, which is a sub 1 plus a sub 2. Okay, so we have a sub 1 was given as 1 and a sub 2 is 2. So that's 3. So what I'm starting to see happen is that it's taking the previous two terms and adding them together. So if we're starting to recognize that now, I don't feel like we necessarily have to keep plugging them in like that. If I'm starting to see the first terms, 1, 1, 2, 3, now to find a sub 4, I'm just going to add the two previous terms, so 2 and 3. That'll give me 5. Okay, then I have a new term up here. So I'm going to add the previous two terms, a sub 3 and a sub 4, 3 and 5, which gives me 8. So some terms, if I was to keep going, it would be 5 plus 8, which is 13, and then 8 plus 13, which is 21, and so on and so on. You would just take the previous two terms and add them together. So what I really want you to get out of this specific example is to how to follow the rule for a sub k involving previous terms instead of just a straight plug in an n value, because you will see this again, the a sub k rules, and you probably will get confused, but just know that it's using the previous terms instead of just plugging in a number. Okay, a factorial. So a factorial is defined as n exclamation point is what that looks like. In math, it's a factorial. And that's taking the n value that has a factorial after it, and you're multiplying that by every number previous all the way down to 1. So that's where we have the n minus 1, and then it's going to keep going all the way down to 1. And then the special case of 0 factorial is defined as 1. So example A, 3 factorial is 3 times 2 times 1, which is 6. And 5 factorial, 5 times 4 times 3 times 2 times 1. Again, taking that whatever is next to the factorial and multiplying it by every term all the way down to 1. That is 120. So now we're going to be using the factorial in rules for sequences. There is a button on your calculator for a factorial, but it's going to be more helpful for us to know the process of multiplying down like that than it is going to be for just typing the numbers in. So here's what it's going to look like if it starts anywhere else. Remember, I said it will specify if it tells you to start anywhere other than 1. This is telling us to start at 0. So a sub 0 is 2 to the 0 over 0 factorial, or 1 over 1. A sub 1 is 2 to the 1 over 1 factorial, 2 over 1. A sub 2 is 2 to the 2nd over 2 factorial, 4 over 2. That one's also 2. A sub 3, 2 to the 3rd over 3 factorial. This is 8 over 6. If it simplifies, there's a fraction. That's a fraction. If it simplifies, please do so. This is 4 over 3. And a sub 4, 2 to the 4th over 4 factorial, 16 over 24. Again, that simplifies, so please do so to 2/3. Okay, but that's nothing different than the other sequences, other than the fact that there is a factorial involved. The reason I say not to use the calculator is because you're going to have some factorial expressions to simplify or evaluate, like looking at letter C here, that does not involve numbers. So you need to understand what a factorial represents as opposed to how to type it in your calculator. So on A and B, I'm going to write out everything, and then we're going to use those strategies to figure out letter C. On A, we have 8 factorial on top, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is just 2 times 1. And 6 factorial is 6 times 5 all the way down to 1. And I am seeing the reason for writing everything out is because now I see that 6 times 5 all the way down cancels out on top and bottom, which makes this a not so difficult problem. What I'm left with is 8 times 7 on top, which is 56, and 2 times 1 on the bottom, which is 2. And that simplifies to 28. Using the same strategies on letter B, 2 factorial, oh my goodness. 2 factorial is 2 times 1. And 6 factorial is 6 times 5 all the way down to 1. On the bottom we have 3 factorial, 3 times 2 times 1, and 5 factorial. Using the same strategies from letter A, canceling whole groups of numbers at once, I see 5 all the way down on the top and bottom. They'll cancel all at once. And I also see a 2 and 1 on top and bottom, so those will cancel as well. I'm left with 6 on top and 3 on bottom, which is 2. So I wrote out all of that, even though I could probably do some of it in my head, because letter C is not giving me numbers, it's giving me variables. So I have to understand what a factorial is to simplify that. N factorial, starting at n, I multiply by every number prior to that, all the way down to 1. So I subtract 1 from n to get my next term. It's n minus 1. And then I subtract 1 again to get the next term, be n minus 2. And that's going to keep going all the way down to whatever, where 1 is from, we don't know n, so we don't know how many terms that'll be. And then on the bottom, it starts with n minus 1, and I subtract 1 to get the next term, so that's n minus 2. And that one keeps going, n minus 3. And I'm going to do the same kind of deal. I see n minus 1 all the way down to 1 is going to cancel on top with n minus 1 all the way down to 1 on bottom canceling. So all I have left is n. Okay, so seeing now we have a summation notation that's going to differentiate a sequence from a series. A series is still a rule that tells us what the pattern of numbers is going to follow, but we know that we're going to have to add those numbers up. It's going to be one single answer instead of a list of answers. So the rule is our a sub I. That's going to be the same thing. It would look the same as a sequence rule. Starting with 1 is the number we're plugging in first, that bottom number. And n is going to be our stopping number. So we're going to add up all the terms from 1 to n, and we're going to get one answer. So this is what they look like. We have the rule 3i, starting with 1 ending at 5. So that's 3 times 1 plus 3 times 2, all the way up to 3 times 5. So instead of listing 3, 6, 9, 12, and 15, we are going to add all of those up and get one answer of 45 for our series. Here's another one, 1 plus k squared. This one's starting at 3. So 1 plus 3 squared is our first term, ending at 6. Oops. And then I add all of those up individually and get 90. Okay, last one is a factorial expression for our rule, 1 over n squared. So we're just going to plug in all of the n value starting at 0, ending at 8. So some of those are going to give you some pretty big fractions on the bottom, or if it gives you only a decimal, then you have to write that down. But this is going to, when you add them together, approximate to 2.71828, which hopefully you can recognize from the chapter we just finished on logarithms and exponentials to be an approximation for e. Okay, properties of summations. They're all pretty self-explanatory. The one that we will probably be using explicitly would be number 1. The summation of a constant from 1 to n is that constant times the upper level n. So c times n. The other ones are pretty self-explanatory. So here we have finding the sum of a series for the series 1 to infinity of 3 over 10 to the I. Find the third partial sum and find the infinite sum. Well, we don't know how to find infinite sums. That would take us the rest of our lives. So what we're going to do is find the third partial sum first and look for a pattern, and then we know that that pattern would continue infinitely. So the third partial sum, what that would look like is I equals 1 to 3 of 3 over 10 to the I. So 3 over 10 to the first plus 3 over 10 to the second plus 3 over 10 to the third is our partial sum. 3 over 10 to the first is 3/10, or 0.3. 3 over 10 to the second is 3/100. And 3 over 10 to the third is getting, is 3/1000, which is 0.003. So we see that there's an extra factor of 10 added into the decimal place every time. So this is 0.333 for our third partial sum. And if we can imagine that continuing infinitely, then we would have an infinite number of 3's. So we'd have 0.3, 0.03, and that would go on forever and ever. So instead of being 0.333, it's going to be 0.3 repeating, or 1/3. So not that we know how to do necessarily any infinite series right now, but we can follow a partial sum like part A to figure out what the pattern is to figure out an infinite sum. And the last thing we're doing is an application. If we're doing an application of sequences and series. This is the resident population of the United States approximated by the model A sub n from 0 to 31, where n equals 0 corresponds to 1970. If we're finding the last 5 terms, last 5, not first 5 as we've been used to doing here, that means our last term is going to be for 31. Then we'll do 30, 29, 28, and 27 is where we'll start instead of A sub 1 like we're used to. So for n equals 27, we're going to plug 27 in for the n in both locations. And this approximates to 272, which is millions of people. And 27, since n equals 0 is 1970, that is approximating for 1997. Seeing what it looks like plugged into 1, I'll just give you the answers for the rest instead of showing the work, but you're just going to be plugging in 28, 29, 30, and 31 the same way that we plugged in 27. So A sub 28 is going to approximate to 275.1 million. That's in 1998. A sub 29 is 278.3 million people, approximated for 1999. K sub 30 is 281.6 million for 2000, and A sub 31 is going to be 284.9 million, which is an approximation for 2001. Okay, so that was it for section 1, 8.1 on Intro to Sequences and Series.